All right, so we're going to talk about scatter plots, which is basically talking about bivariate data. Previously, we talked about univariate data, but now we're moving to bivariate, and you're probably saying to yourself, hey, but Mr. Spencer, what we've talked about before had an X and a Y, and that's bivariate. And I go, well, you're right that it had an X and Y, but it's not truly bivariate, and here's why. When we were doing it, we had something on the X, a variable on the X axis. Maybe it was height, maybe it was weight, maybe it was grade point average. It really doesn't matter. And then on the Y axis, we had a counting. How many people had GPAs of that? How many people were this tall? Okay, so the Y was purely a counter and the X was some variable. With bivariate data, we have basically an ordered pair, an X and a Y that are tied together. Perhaps we tied, for a single person, we tied their height and their weight together. Maybe their weight was the X, their height was a Y, and we plotted that single point. And so for every person, we would plot essentially one point that it was measured by two variables, height and weight. Generally speaking, we talk about the X variable as being the explanatory variable, and that's kind of easy to remember because explanatory has X in it. And basically, this is like Algebra 1. The explanatory variable is the input, whereas your response variable, the Y, is the output. And the very fact that we're talking about inputs and outputs would indicate that the X variable would be useful for predicting the Y variable, or we believe that it may be useful for predicting the Y variable. All right? So here's a scatter plot of ages of a husband and wife, and basically we look at it and go, hey, it's increasing. And so you're going, generally speaking, not completely, but as the age of the husband increases in general, the wife's age increases as well. So an older husband equals an older wife. A younger husband would be equal to a younger wife. Now, that's not 100% the case, because we know we have men who have trophy wives, and we have women that we refer to as cougars. And I may not be the most appropriate term, but it is the way we talk about it in today's society. And in fact, I've actually marked a red dot, which is an extraordinarily famous couple. And basically, you all know who this is. It's Donald and Melania Trump. He is substantially older than she is. Okay, and that red dot basically points to where they are. And as you can see, that they're not really in that group together. Okay, all right. But in general, we can say as the husband is older, the wife is older as well. So we went about and we hopefully input all this data into the calculator, and I want to talk to you about this. And we had some students put together a video. And by the way, are y'all seeing the calculator on the screen right now? Awesome. So I want to make very clear that you need to make sure your stat diagnostics is turned on. It's not very difficult to do, but you need to make sure it does, because it does a lot of work for you behind the screens when it's on. So we have mode. We're going to arrow down until we see stat diagnostics. Then we're going to arrow one to the right and press enter so that it's turned on. Also below that, we see stat wizards. Personally, that's what I want to be, is a stat wizard. I think that would be way cool to be a stat wizard. So I'm not sure what that is, but leave it on, okay? So stat diagnostics is turned on. We're going to go press second quit. We've input all this data into stat edit. I'm going to go ahead and clear out my column 3, but everything, all of our X's, which is our distance flown, is an L1, and our airfare, what we're charging, is an L2. So these are our X's and these are our Y's, okay? And I want to go ahead and create a scatter plot for this. Well, the first thing I want to do is go to Y equal, and whatever's in Y equal, clear it out, because it's likely to mess you up in the long run. So if you have anything anywhere in Y equals, please clear it out. Then go to second stat plot, and ideally everything is off. 2, 3, and 4 are off, and we're going to turn 1 on, stat plot 1 on if it isn't already. To turn it on, I'm going to arrow over to the left and press enter. Now I'm going to drop down 1, and I want the very first graph, and you all probably have box plots highlighted because that's what we were working with. So we're going to press enter and make sure that we have that first graph, which is a scatter plot. Then we're going to drop down and press second 1, followed by second 2, where my Y is. At this point, I'm going to press zoom 9. Now, the fact of the matter is, I know some of you press zoom 9 and it's stuck. If that's you, go back, just press the clear button, and now press zoom 9. And it should work for you at that point. So hopefully that worked for everybody. And you have a graph looking like that, and there's your scatter plot of airfares. And in general, I kind of see a trend going up. All right, I see a trend going up, and that's my scatter plot. And by the way, I should have done this already. I forgot to do this, but I'm going to do this now. Let's verify that we have our data entered correctly, because if we don't, we're going to get stuck later. To do that, I'm going to go to Stat, Calc, One Variable Statistics, and I'm just going to look at column L1, and I see that I have 853.7. Yay, I have 853.7. That's good. Then I'm going to check my standard deviation, 497.8, 497.8, and I'm all excited. But immediately, some of you are going, but Mr. Spencer, why did you use S of X when you could have used sigma X? And that's what I like about this class. You always ask the questions I want to answer. The reason I chose S of X is it represents a sample. And basically, this is not all the airfares. This is not all the flights. This is just a sample of the flights. So because it's a sample, I use S of X. Had it been all the airfares or all the flights, I would have used sigma, okay? Now, I've checked the first column. Let's go ahead and check our second column. So stat, calc, one variable statistics, and now it's L2, so second followed by the number 2. And we have 244.33 and 56.37. So we're fairly confident that we have everything correct. And also, we've also done the scatter plot, so we're ready to move on to the next page. All right, in the next page of notes, we're going to fit a best fit line to that. So basically, our scatter plot looks something like this, and we're going to fit a regression line to it. And basically, that means we're going to minimize the distances from the line. We're going to minimize the actual values from the line. And most of you could probably draw a line and be pretty close. And you're going to see that when we use the calculator, it does it fairly well also. Now, I'm not going to read all the notes to you because I believe that you can, but I'm going to talk to you about a couple things. First off, essentially we're going to work in slope-intercept form, y equals mx plus b, just like you did in Algebra 1, except we can't leave well enough alone. We have to dink with things a little bit and change it up just a little bit. So instead of y equals mx plus b, we're going to do y equals b plus mx. All right? And you're like, why would they do something stupid like that? If you were here, I would show you. If we have time at the end of class, I will show you why. There's actually a very reasonable reason why. It actually makes good sense. It's logical. But we're going to do y equals b plus mx. Another thing I need to talk to you about is you'll notice I have y written here. And over here I have y hat. And there is a difference, and it matters. Y is the actual value. Y is what we actually observed happen. Y is reality. Y hat is what we predicted to happen. It's what we expected to happen. It's what our model showed us we thought would happen. So y is what really happened. Y hat is what we predicted from our model to happen. And it's really, really important that you don't mess those up, because AP will ding you a point for that. All right? So y is reality, y hat is what we predicted to happen. Okay? All right, so now we need to calculate the best fit line, the regression line. And it's very simple on the calculator. So we're going to press Stat, Calc. I want you to choose number 8, or linear regression A plus BX. I know there's another one at number 4, but I want to do A plus BX because I want to do y-intercept plus slope. All right? So I'm going to drop down to 8. My X list, which was my distance, is an L1, so second 1. My Y list is an L2, so second 2. I don't have a frequency to deal with, but then I need to store the regression equation. This is super, super, super important. Not difficult, but super, super important for all your other work. So press alpha, followed by the word trace. So alpha followed by trace, then press enter. It should say Y1. It's storing that equation for you in Y1. And now we're going to press enter a couple times, and we get a ton of information. We get a y-intercept of 177.21, a slope of 0.0786, r squared, whatever that is, and we'll talk about that in a moment, of 0.48, and an r of equal to 0.69. Okay? So those are my check values. And now I'm going to press zoom 9. And sure enough, it fit the regression equation. It fit that line of best fit to my data. Okay? So there we go. We've now fit, that's our line of best fit. This line is not reality. This is what I predict to happen. You can see that I predicted pretty closely here and here, but I had some predictions that weren't so close. Okay? Remember, data ain't perfect. Real life ain't beautiful. It can't all be like me. Some of it's way off center. Okay? I know you're saying you're way off center, Mr. Spencer. Truth be told, that's the truth. All right. And what's it called when it's way off center like that? Anything that's away from where it's supposed to be is called the error, or we like to refer to it as the residuals. All right? The residuals it basically measures how far actual reality is from what we predicted. So in this case, reality is a long way from what we predicted. Over here, reality is really close to what we predicted. Okay? And we have positive residuals and we have negative residuals. Because the residual equation, which is super important that you actually learn this, is observed minus expected, actual minus predicted, reality minus predicted. So I like to use observed minus expected because I know it'll help you with chi-squared later in this class and in biology. So I like to use observed minus expected. You don't have to. You can use actual minus predicted or whatever. But regardless, it's y minus y hat, the real value minus the predicted line. So this vertical distance, and it's a vertical distance, is my residual. And if I add all the residuals together, I have some that are positive, I have some that are negative. Not surprisingly, when I add them all together, they sum to 0. All right, they end up equaling 0 when I sum all the residuals together. Okay, so as it turns out, besides just being, okay, there's my errors, that's how much I'm off by, the residual plot, we can actually make a graph of the residuals, which we haven't done yet. And I'll show you how in a moment, has a great benefit. Because the residual plot lets me know whether my model is appropriate. Is this the best model, or might there be some other that is better? How do I know? Well, that's what I like about you guys, always asking the questions that I need to answer. If my residuals are completely random, and that looks pretty daggone random to me, I have no idea whether the next point's going to be above the line or below the line. I don't know where the next point's going to be. If they're random, then I have the appropriate model. If they are random, I have the appropriate model. However, if I have a residual plot that has a pattern like this, there's another model out there that's more appropriate. What it is, I don't know yet, but another model is more appropriate if my residuals have a pattern to it. This one right here, they also have a pattern, because as you move further in a positive direction, they're converging to 0. So I know that when I get way out there, they're going to be really, really, really close to 0. So there's obviously a pattern to that. So what I'm looking for is a residual plot that's random. So let's go ahead and make the residual plot. All right, so we're going to go back to our favorite stat edit. And I'm going to go to the top of L3. And now I'm going to press second list. If you do that, somewhere on this list, resid should pop up. If it doesn't, that means you didn't turn your stat diagnostics on. If your stat diagnostics aren't on, you're not going to have that show up. If you didn't store it in the regression equation, that's not going to show up. So I turn that on and I go all the way down. In this case, it's on number 8. I think a lot of times it shows up on number 7, but regardless, it's showing up on your calculator somewhere. Select that, press enter, and now we're going to press enter again, and it populated all my residuals. That's how far off I was. Sometimes I was off by a lot. I was off by 60. Sometimes I'm pretty close. Okay? But now we're going to create the residual plot. And the residual plot that we're going to create looks like this one at the very far corner of page 204.
Mr. Spencer?
Yes.
I'm still a bit lost. So to get the residuals...
Let me go through this, finish this up.
Okay.
So second, stat plot, press enter, arrow to the left, drop down, highlight the very first graph. Now my X list isn't changing, but my Y list is my residuals, which is an L3. So I'm going to press second 3, and then I'm going to press zoom 9. Once again, if you don't get a graph, press clear followed by zoom 9, and it should pop up. Now, how random is this? Because you're sitting there going, I have a bunch here, and it's like, well, I have a bunch there because I have a lot of data points taken there. I don't have many data points here, but I don't care where you put my cursor. If I put it here, I don't know if the next one's going to be up, above, or below. Same with here. I have no way of predicting where that's going to be, where that next one is going to be. Okay, so that's the residual plots. Then we need to talk about correlation. All right, so we've already actually calculated the correlation. When we went and did stat calc number 8, and we had L1, L2, and the alpha trace, we got an R. That R value is my correlation. And it tells me how strong of a linear relationship I have. And we have an R of 0.69, and you're like, well, how strong is 0.69? That's a really good question. Well, first off, let me tell you a little bit about the correlation coefficient. First off, remember, correlation does not mean causation, all right? It does not mean causation. Correlation can lie within the interval -1 to +1, all right? It can lie in the interval -1 to +1. If we have a correlation of -1, that means we have a negative slope. We have a negative slope, and every single data point lies directly on the predicted line. It's a perfect correlation, all right? If we have a positive one, we have a positive slope, and once again, every single data point lies directly on the predicted line. If we have zero, a correlation of zero, we have nothing. We have a blob of dots that makes no sense. We don't see a relationship, or excuse me, we don't see a, let me rephrase that. We do not see a linear relationship. There might be some other relationship, but we don't see a linear relationship. So positive one, every dot lies on a line with a positive slope. Negative one, every dot lies on a line with a negative slope. Zero, there's not a good linear relationship. But your question was not about that. Your question was, well, how good is 0.69? And I'm just going to say there's some rules of thumb. These are not exact. These are not complete science, but they work for AP and they're what I use. All right? Or they're what I use for AP purposes. If the absolute value is greater than 0.75, if your R has an absolute value greater than 0.75, we say that there's a strong linear relationship. So in other words, if you have a positive 0.8, that's a strong linear relationship. If you had a negative 0.9, that would be a strong linear relationship. Anything where the absolute value is 0.75 or greater, we say is strong linear relationship. Anything between 0.4 and 0.75, we say there's a moderate linear relationship. And anything less than 0.4, we say is a weak linear relationship. Okay? Now, once again, just because you have a high correlation or a high association does not mean there's causation. It can be highly related, it doesn't mean it's causative. And just because we have a small r doesn't mean they're not highly correlated. For instance, I have a parabola, and it happens to be a perfect parabola. And I can give you an x, and you can tell me what the y is going to be. So it's very highly related, but it has a very low linear relationship. Because truthfully, when I look at this, am I better off drawing a horizontal line, a vertical line, a diagonal line? I don't know. There's no good way to make a predicted line with that. The parabola would have been the more appropriate model. Same with this oval here. All right? Just because R is low doesn't mean there's not a relationship. It just means there's not a strong linear relationship. So R is a measure of linear relationship. Okay, so we have a bunch of definitions, or excuse me, we have a template, I should say, that we use for, we have a template of sentences that we use. If you were here in class, you would be expected to memorize all of these and write them out on a test. And quite frankly, on an AP exam, you would be as well. However, since we are online at this point, you're not going to have to memorize them. You can just use the template during the test. All right, so it'll save you some time on memorization. I'm going to use this template to help me answer some questions on the following page. All right, so looking at page 207, we're still working with the same data. And this is the type of stuff that they're going to ask you to do. And a lot of it's based on Algebra 1. Define X. Oh, well, it's the distance traveled in miles. That's just like not rocket science. Y is the fare charged in dollars for a given trip. And then we have Y hat. Notice I used Y hat. The reason I use the Y hat is because that is the prediction line. It's not the actual line. We don't have an actual line. This is our line of best fit. And so Y hat equals 177.21 plus 0.0786. And in case you forgot, that's what I got when I ran the linear regression with the calculator. 177.21 was my y-intercept. 0.0786 was my slope. And just like in Algebra 1, we need to define our slope. Please do it the way they taught you in Algebra 1. So the slope is $0.0786 over 1 mile. By the way, decimals over a whole is perfect, perfect for our class. I know the math teachers will scream and holler. We're more real life, okay? We like this. So for every 1 mile increase in distance, there's a $0.0786 increase in fare. That sounds just like the stuff you used to do in Algebra 1, I bet. All right. Then it says find the y-intercept. Well, we already did that. And the y-intercept is 177.21. And now we need to define it in context. Sometimes it makes sense in context, other times not so much. This is probably a not so much case. But it basically means if I were to step on that airplane, I would expect to have to pay $177.21 to step on that airplane and fly nowhere. I don't think anyone steps on an airplane to fly nowhere, but if it were to travel 0 miles, this is what we'd expect. Now, why is that? It's because there's certain costs. There's cost for it to be parked at the gate. There's cost for it to be at the airport. There's cost for maintenance, regardless of whether or not it flies or not, okay? The next thing it tells us to do is to calculate S. We are not going to calculate S until Wednesday, all right? But I am going to talk to you about S. Now, it is a fairly difficult concept to understand. It's not difficult to calculate, but not today. S is the standard deviation of the residuals. And in this case, it happens to be 41.82. I'll show you how to calculate that on Wednesday, all right? And measures the variance in fare for a given distance. So let's go back and think about things, all right? When we talked about the empirical rule, we said 68% of the data was plus or minus 1 standard deviations from the mean, yes? We also said 95% was plus or minus 2, and 99.7 was plus or minus 3. Well, we also know that the residual is how far the data is from the predicted line. So let's go back to our prediction line, and hopefully I get there fairly quickly. I know I skipped over it so many times today. There it is. There's our prediction line. So we said I calculated the standard deviation of being 41.82. I'm just going to round it to 42 because that makes it easy for me to talk about. So $42 above the predicted line and $42 below the predicted line, I would expect 68% of my fares to be there. If I doubled that and I went, instead of 42, I went to 84, 84 above the prediction line and $84 below the prediction line, I would expect 95% of my data to be there. And if I went 3 standard deviations, which would be 126 above and 126 below, I would expect there to be 99.7%. So you can basically say, I could draw a parallel line that's 42 above and a parallel line that's 42 below, and I'd say 68% of the fares would be in that range. If I made a parallel line that was 2 standard deviations above, 84 above, and 84 below, would be 95% of the airfares would be in that range. All right? And basically it's because we know that my model is not perfect. So the standard deviations of the residuals is what that calculates. All right, is what S calculates. Next thing was R. Well, we already calculated R. We calculated R on the calculator and said, hey, it's 0.694. And that says there is a moderately strong, because it's between that 0.4 and the 0.75, because it's between 0.4 and 0.75, there is a moderately strong positive linear relationship between airfare and distance travel. I must have the words moderate, strong, positive, and linear in relationship. Those are the key words, all right, between my X and Y, whatever they are. In this case, my X was airfare, my Y was airfare, and my X was distance travel, all right? Very important that you have that. All right, that's the correlation. The next thing is R squared. And to me, R squared is so much more important than R. We call R squared the coefficient of determination. And I think it's a ton more important than R. That said, if you have R, it's easy to get R squared. All right? Because 0.64 times 0.64 gives me 0.482. It's just that simple. All right? Or if I take the square root of R squared, I get R. But the reason it's important is because what R tells me, R squared tells me. It tells me 48.2% of the variation in Y, or in this case, airfare, can be explained by changes in X, which is in this case, the distance of the flight. So 48.2% of the variation in airfare can be explained by distance of the flight. That's pretty important. That tells me how useful my model is, how much of the variation is explained. And you're like, well, if it only explains 48%, then other things must be explaining the rest. And that's probably true. Some airports are very expensive to land at. Some planes are more expensive to fly than others. Some flights are really popular. So those things are going to factor into the price that you pay, okay? Sometimes time of year, etc. The next thing, number 9 says, estimate the fare for a 392-mile flight. Well, that's easy. Y equals mx. Oh, I'll put in 392 for my x, and I calculate $208.03. Or $236. I skipped a line. I'm so sorry. For a 750-mile flight, I plug that in, and I get $236.18. Please note, I used y hat because that's what I predicted to happen. That's not necessarily what happened, that's what I predicted to happen. And we're about to see the difference when we do number 10 and 11. So on number 10, we're traveling 392 miles and they want to estimate the fare. So I put in X and I find out, hey, we expected to cost $208.03. Once again, this is an expected, it's not the predicted. All right, I don't know what we actually paid, but I would anticipate paying $208 to travel that far. And then number 11 gives us a hint as to what's going on. Based on your answer in number 10, calculate the residual for a 392-mile flight. Well, it says to myself, I need to know what residual is. Residual equals the observed minus the expected. Well, we just calculated the expected, that's good. But now I need reality. What did a 392-mile flight cost? And they're like, well, they must have given me that value somewhere. So I go up here to this table and I start looking. And I start looking for a 392-mile flight. And when I get to Orlando, I say, hey, Orlando was $392 and we paid $238. That's what we actually paid. That's not what we predicted that we'd pay. That's what we actually paid. So $238 minus the 208 tells me my residual is $29.70. And notice it's positive, and it's positive because my observed value is above the predicted line. If my observed value had been below the predicted line, it would have been negative. And that is all I want to do. I don't want to